two things. Got it. Okay. Get it away.
Got it, go away.
Hang on.
Oh, that was me.
What happens is that bird legs, first of all, they're very thin. Like, you know, we don't eat bird legs because there's hardly any meat on them. I guess the English eat bird feet, but there's hardly any meat on them. So there's not much really to get cold. That's one thing. The second thing is why is this not working?
Maybe that's because it should be. I don't know. I'll do it nicely. Okay.
Got turned off. I was turning that off and on once. Maybe say go back. No, that doesn't work either. Turn it
Try
off and
facing
on.
the screen.
Hmm?
Try facing the screen. Come back on.
Okay, it's not advancing.
There you go, now try.
Thank you.
Thank you.
So the other mechanism is they have a counter current exchange. Excuse me. Right over here. First, you can see there's not much meat on here. There are veins and arteries going through here, but what happens is that the artery is bringing warm blood down into the foot. Well, instead of bringing all that warm blood all the way down so it dissipates into the water, some of that warm blood goes right back into these cold veins going back up to the heart. So by the time the blood gets down here, it's already pretty cold. And they're warming up the blood going up to the heart. So the core of the bird stays fairly warm, even though the legs are a little bit cold. But again, there's not much to get cold in the first place. But this counter current exchange takes care of the rest of it.
The heat exchanger.
Or they can go into torpor, you know, hummingbirds can do that. They can drop their metabolism and drop their body temperature down several degrees for the evening if it's really cold. When they wake up in the morning and start feeding. And a few birds, like the torwheel, can actually drop their metabolism so far down that they can do it for a couple of weeks. There aren't many birds that'll do that, but hibernate almost for a couple of weeks. Not really hibernation, but they can drop their body temperature down to 40 degrees Fahrenheit for a couple of weeks. It's the only way to get through. If it's really cold, what do these guys feed on? Nectar and insects. There's not much nectar and insects when it's really cold. And then this guy I found out about a couple of years ago. I think these are fascinating. Cormorants. We saw a couple of cormorants toward the double-crested cormorants. This is an Arctic cormorant. These Arctic cormorants live in Greenland and they don't migrate. They're permanent residents of Greenland. If you've ever been to Greenland, you know, it's one big icy island. We went to Greenland, we tried to go to Greenland 6 months ago or something like that. We were on a ship and I was lecturing on the ship. And the only reason we took that cruise was because we wanted to go to Greenland. Well, the weather got bad and I skipped 3 Greenland landings and we ended up in some tiny little town called Korthog or something. Bracelets on the beach. Anyway, so I didn't get to see these guys, but these are Arctic cormorants and they spend the entire winter feeding. They don't hibernate, they don't estivate, they don't migrate. What do? They feed. All they do is they dive in the ocean. You know, it's colder thick out there. They'll eat and eat and eat, and they just eat so much that they can keep their metabolism up. So that's the way to do it. So if you don't want to buy winter clothes, just eat a lot and you'll get to them when you That's what they do. And if it's hot, one of the mechanisms, and you'll see this especially with pelicans and cormorants and a few other ones, panting. Birds have no sweat glands. So the only way they're going to lose heat, they have lungs and they have accessory lungs, which are air sacs through their body, even into their arms, into their humerus. And these air sacs, the way a bird breathes, we breathe in and we breathe out. They're breathing in and out at the same time. So they have a very high, very efficient respiratory system, but also helps cool them off because they're getting a lot of air in and out. And it has to be efficient because they have no sweat glands. So this is the way when they really get hot, they spread their feathers out, expose their skin to the air and pant. And with pelicans and cormorants and a few other related birds like that, it's called, and chickens do this too, gular fluttering. Their throat just flutters back and forth like that, like this, and it's just exposing again their skin to the air and getting the cooling effect from it. Storks and vultures and a few other ones do this. They defecate on their feet. So defecation and urination are all in one with birds. And the reason is they don't have urinary bladders. They don't want to carry water around with them like we do, except for ostrich. Ostrich and emu and cassowary do. But all the other birds have no urine. They get rid of the water. They get rid of it with their poop at the same time, dump everything out on your car. Even though it is acid, though there's some studies on this, even though it is acid, that's not what hurts your car paint. What it does is this thing is very strong physically, this stuff. When it lands on your car, it starts to dry, and as it dries, it pulls the paint with it. So you don't need any acid or any special chemicals. All you need to do is get that off as soon as you can. Anyway, that's not why birds do that. What they do this, what they do is they defecate on their legs to cool their legs off. So the legs get warm. They've got the counter current exchange going. But this helps a little bit with cooling because there's just some fluid, just like you were throwing water on your arms or legs to cool yourself off. And in the case of storks and in vultures, it also is a way to keep bacteria off their legs. Storks, as you may or may not know, are related to vultures. We used to think they were related to cranes, but DNA studies showed that it's related to vultures. And a lot of them look like, they have, this one's not bald, but some of them have bald heads. They're really ugly birds, and they eat a lot of garbage. You see them in Africa, in towns eating out of garbage pits. And this keeps the bacteria off their legs as well. Not very pretty, but it works. And then, of course, birds have to take care of their feathers, and they preen themselves. And the reason, and they lose their feathers twice a year. Typically, they get new feathers, and the other feathers wear out. And then they have, and I don't have a picture of it here, but right here is a uropygial gland or preen gland or oil gland. This is the Pope's nose you take off a chicken. And what they do is they squeeze that, oil comes out, they get it in their bill and they rub it through their feathers. It keeps their feathers oil waterproof so they can go in the rain like this. And but they have to keep doing that, and they're always pecking at themselves, cleaning themselves up. Sometimes birds will clean each other, of course, like parrots will do that. And then maybe you've seen this behavior. This is a northern flicker. What they'll do is they'll lay on the ground. Flickers do this especially. They'll lay on the ground on an ant's nest. I don't know if they do with fire ants. It's a good question. They'll lay on an ant's nest, and then they'll let the ants crawl over them. And then they pick up, and one ant at a time, they'll pick up one ant at a time, squeeze it and rub it through their feathers. And the reason they do that is ants contain what? Formic acid. Formic acid is parasite. It deters parasites. So they rub that through their feathers, but they'll do it one ant at a time, laying on there. They're not eating the ants. The ants are not doing anything to them. They're not clearing out the parasites, but the bird itself rubbing himself with anti-parasite lotion, sort of. And this is what it looks like when a robin does that. It looks like they're being irritated by the ants or doing something funny. They're just really using the ants. Lots of birds do that. And if you look at the ornithological literature, you'll see that birds do that with various things. And there was one paper I read about a bird using a mothball, rub the mothball through his feathers. And then it got to be a joke among a bunch of ornithologists, and people would publish papers like a flicker ant with bowling ball. They do with various kinds of things.
Oh, my
And then,
God.
of course, birds have to eat. I mean, that's their whole purpose when they're not reproducing, is they're going to eat and protect themselves against predators. Those are the two things they have to do now. So here's long-billed curlew looking for food. You wonder with this little 6-inch bill what they're seeing down there, sticking it in the mud. Where's the food? That silt down there, they can't see anything. He got something. How did he do that? Well, this is the bill. And on the bill, not exactly on the bone, but there's a covering on the bill called a rhamphotheca. You know, birds have this covering over a bill. And just under that are these things called Erb's corpuscles. And these Erb's corpuscles are little sort of cells or sensory cells that sense pressure. And so they're all over the bill here. So they put their bill down into the muck and they can sense the pressure. If there's something over there, there's a worm over there, there's nothing over here. They put their bill in the middle. They can't see, but then they know there's something over here. They can sense the pressure is more over here than it is over here. So the second time they move over and push it over there, they find it. So they can just go blindfolded, keep sticking their bill in there and find food. But Erb's corpuscles, lots of birds, ibises have that. Almost all shorebirds have that. A lot of other birds have those corpuscles. Not only that, you've got the bill way down in there. You think if you were you're down here trying to get something too, you have to open up the whole bill. You're opening it up against all this muck. You can't do that. I mean, think about opening up, your hands like this. You want to open up just the tip, and that's what they do. Shorebirds like this open up just the tip of their bill. They have a special mechanism. It's called kinesis. That the muscles of the head and the bones of the jaw allow them to push the upper bill up and the lower bill down, so they open up just the bottom of the bill, or just the end of the bill.
Wow.
We have a Dowitcher doing the same thing. Probably never noticed that because you don't see them that closely, but that's how they're able to feed. And then among a lot of blackbirds and starlings and other birds, they undergo gaping. This is a gaping mechanism. What they do here, not just poking their bill in the ground, but they poke their bill in the ground and open it up. They have stronger starlings, blackbirds, and a few other birds have stronger bills to open, stronger muscles to open their bill and close the bill. Just so they can open that hole up in the grass. And then flycatchers. I was talking to Betsy and Tom about my early research when I was in the graduate school in the Mesozoic. Something in a book about the rictal bristles. These are rictal bristles, and most birds have these little bristles on the sides of. And it said in this book, they use that as a trap so that when they see an insect, they're flying along, the flycatchers are flying along, they trap an insect and push it into their mouth like this. So it seemed to make sort of sense. But I thought, I don't know, that's not quite logical. So I took that on as a research project and I built a big cage, probably half the size of this room with a big glass front on it, caught some flycatchers, and then trained them to catch flies. I bought some flies, from us, Flies or Us, or whatever. Put it in a little tube and I blew them into the cage. Once in a while I ate one, but they were all sterile. But then the birds had learned to come down and catch the insect, and I filmed them at 400 frames a second using film at that time. So I could tell what they were doing. And they always caught flying right at the tip of their bill. See the tip of the bill here? Got a little bend in it. Help to catch the insects. They don't use those rictal bristles at all. So that was sort of a myth that went on for a long time. After that, people then wondered what do they use the rictal bristles for? Well, it's for a kinesthetic sense. They fly, and if they're turning like this, it tells them they're turning left, turning right, going up, going down, going fast, going slow. It's just a mechanism for orienting themselves in the air. And we know that because birds are really good flyers, have a good set of rictal bristles. Birds that don't have that. And also there are nerve connections going from the rictal bristles to the control center of the brain, the cerebrum. First time, cerebellum. And even bald eagles have these things, and bald eagles aren't catching insects. And kiwis have rictal bristles that long. They're not using it for flying, but just so they can orient themselves in the dark. There we go again. Advance the slide once. There we go.
Oh, wow.
And lots of other birds have mechanisms for catching insects as well. This, of course, is a puffin. And they have birds don't have teeth, but they have little serrations on the bill. And this is, a bunch of them, and they'll get those serrations. They can catch one fish after another, keeping the other fish in there because they're going out maybe 10, 12 kilometers, catch fish to bring it back to their young. I'm not going to do one fish at a time. The record, at least as far as anybody's taken a picture of it, of a puffin has 54 fish in its bill. And then maybe you're familiar with these guys, the black skimmer. They skim along the surface of the water.
Yeah, they can fly like.
Hopefully not hitting a piece of driftwood and snap on fish or squid or something like that. When these birds are kept in captivity, they have to, the keepers have to file their bill down because that lower bill keeps growing all the time because they do wear it out doing this.
Whoa,
Got it. Look at
And then the osprey, osprey, they're all over the world, very successful birds. They have prickles on the bottom of their feet when they catch a fish. They can really hang on to it. But also than that, when they're flying around, they have two toes forward and two toes back. But when they catch a fish, it's one toe. No, I'm sorry. When they catch a fish, they have two toes forward, two toes back. When they're perching, they move that toe back again, so they have 3 and 1, like most birds do. On the action of this.
After hitting the water and grabbing the fish, the game still isn't over for the osprey and its quarry. He needs to get airborne again. His talons are equipped with adhesive scales and long curved claws for an unbreakable hold. But a big trout can match him weight for weight, and the instinct of the fish is to swim down. There are tales of weak and hungry ospreys being dragged to the bottom, unable to release the fish or lift off from the water successfully. But osprey wings are adapted to give maximum lift from the water.
Can they release them?
And this male is young and strong. This is a struggle he's destined to win.
That is amazing. Like surfing. It's a big fish.
And to orient the fish so the head is the same way as the osprey, so it's aerodynamic.
Photos, yeah.
And then, of course, hummingbirds on the other end of the spectrum. Hummingbirds are feeding on nectar. They do eat insects when they're breeding because they need protein, but most of the time they just need the carbohydrates. So they're feeding on nectar. But how do they do that? Now, this is a really nice high-speed motion picture of some South Africa. I think they were, I think this was in Colombia. But as you'll see a little bit closer up, tongues of hummingbirds are sort of like a mop. They're shredded at the end, and birds they stick their tongue in there, and it soaks up by capillary action on the end of the bill, and they pull their tongue in, and it gets squeezed out like a squeegee, and then they suck the nectar down.
Awesome.
Doing that very quickly.
Oh, look at
See,
that.
there's a tongue. There's all kinds of different mechanisms of or different adaptations of hummingbird tongues. There are 350 kinds of hummingbirds and 350 different kinds of tongues, but they all work the same way. Okay, well, birds have to have senses, you know, smell and taste and so on, to implement all this adaptation. So let's look at a couple of those. This is my wife. We were in Australia. This is up in a place called Murphy's, I think it was, about 36 miles of windy road all the way up in the mountains. When you get up there, all these birds come after you. This is our little motel room we had up there. As soon as she got on this was like 5 minutes after we arrived. As soon as she got on the patio, these birds hopped off.
Yeah.
We're supposed to feed them, but there's no way I'm going to get Carol not to do that. So there's a king parrot, a bowerbird, and a cinnamon or a rosella, crimson rosella. And what this tells you is that obviously birds find color, their eyesight really important. And now we know after the last 20 years, we used to think that feathers came from scales of reptiles, that they're just elongated scales, and the scales became ways of insulating birds. It's not true. Feathers, now we know, are totally new adaptations by dinosaurs, early dinosaurs. These feathers the reason we know that is that these early dinosaurs couldn't fly, but they had feathers covering them and they had color patterns. So the feathers must have first evolved as signals, as color signals to males, females, different species, and so on. And only later they got the function of flight and insulation. So here, obviously, there's a lot of communication color-wise going on. And birds have really good eyes, really good eyesight. But different kinds of eyesight. We have pigeons like this, doves and pigeons that can see you know, sort of like this on either side of them, but they can't see very well in front. So like this, we get a pigeon that can see all the way around, almost to the back, but right in front, they only, so they have monocular vision, but binocular vision only right here. On the other hand, we get an owl that has this binocular vision like this, and only a little bit on this side, but then again, they can turn their heads 270 degrees. If you think about it, this is monocular vision here, but that's still pretty good. Our peripheral vision is like this. I can see my hands, see my fingers move, but then back here I can't. Pigeons can see all the way back here, so they may not be able to focus, but they still have an idea of what's going on. And the size of owl's eyes are huge. I mean, they're like 1/4 the size of the skull. For obvious reasons, they've got to pick up a lot of light if they're going to be hunting in the dark. And in fact, they're so big that this is the ear of the owl. Right here. That's the ear hole of the owl. And the eyeball is back here. So the ear goes the eye goes all the way back to the ear. Have you ever seen the ear of an owl? They look just like ours. They're underneath the feathers, so you don't see them. And they're oriented differently. One's here and one's here, and they're shaped a little bit differently. And the reason is that when and I do this, I won't do it now, but I do this trick where I tell somebody, I'm going to snap my finger over your head. You close your eyes and tell me whether, I'm going to snap my finger somewhere around your head. Tell me it's in front and back or over your head. And most of the time people don't get it. Sometimes they do. And the reason is we hear sounds like this coming in this plane. And the only way to locate it is to turn your head. Owls already have their ears in different places, so they can locate it immediately without turning their head. One time, a woman in the front row did that and she knew where it was. I did it like 3 times. She always got it. So how can you do that? She says, I'm blind. I didn't think of anything watching a slideshow who was blind in the front row. Be really sensitive to the sound. Other than that, most people don't get it. And birds can see ultraviolet. They can see the 3 colors we can, the 3 primary colors, red, yellow, blue. They can see the visible spectrum like we do. But they can also see ultraviolet. We've just discovered that in the last 20 years. So what good does it do to see ultraviolet? And this is why you put ultraviolet stuff on your windows to keep birds from running into it, because they can see that. We can't, so we can see through it, but they might stop, we hope, without running into the window. So we're still figuring this out, but what can birds see? What we see is cockatiel is like this, but possibly what birds see is like this. What kind of marking? We don't know that, we're just speculating. But we do know something like this. Here's an saw-whet owl. This is what we would see, but if you put black light on it, so it reflects UV, it looks like that. So an owl like this, northern saw-whet owl flying through the woods, is signaling to at least some other birds that he's there, while other birds wouldn't see him, or we wouldn't see him, or other predators. And then here's a European kestrel hovering, looking for prey. How does it find its prey? Well, they prey on voles, little mouse-like things. We have voles here too. And the voles are going through the snow, leaving tracks, leaving trails here and there. You wouldn't necessarily see them, but this is a picture when you can see them because it's got the snow. But as they go, they're marking those trails with urine. They're peeing all along the way. And the urine reflects ultraviolet. And the fresher it is, the more ultraviolet it reflects. So the hawk is above there looking around and following these ultraviolet tracks like that till he gets to the mole.
Wow, there it is.
And then, at least in a couple species of birds, we found out that, okay, there's these little birds in there. How does mama know which ones to feed? In one case, these are African starlings. In one case, the bird that needs the food the most has ultraviolet. So the more ultraviolet they have, the hungrier they are, the more they need the food, and the parents feeds those. In another case, some other bird, I forget which one it was just the opposite. The ones with the least ultraviolet are the ones that were the hungriest. So we just need to do a lot more testing. Okay, so as you would expect, some guy with commercial ideas is going to just take us science up on that and say, okay, well, let's use, if birds can see these things, how about painting your decoys with ultraviolet? The problem is, you don't know what the birds are seeing, so you're hunting a goose and you paint the goose's head with ultraviolet, the decoy. You don't know what the bird, bird might be flying over and go, oh, look at him, and give you the finger. Whatever it may be, it's not it's a wrong signal. And we know, for instance, here, these are blue tits from Europe. The males have these blue caps and they reflect ultraviolet. Females' blue caps don't. So that's they're signaling sexes in that case. So what do we know? We know in this case, but lots of cases we don't know.
They know the boys from the girls.
So there's a special problem with birds that are hunting in watery environments. You know how you look through the water and then you see a fish? It's not really where you see it, it's somewhere over here because the light refracts as it comes through the water and bends it. So what the bird is seeing is not necessarily where it is, except that birds have an oil droplet right here in their sensitive cells in the retina. They have an oil droplet. Now, if none of you use an oil microscope, this thing called an oil immersion microscope. Regular microscope, you're 200, 300, 400 power, you just look through it. Okay, but when it gets to be like 1,000 power, it starts to scatter everything. And so you put a drop of oil on top of the slide. And then it'll straighten, it's just like wearing Polaroid sunglasses. In your kind of glasses, but mostly sunglasses. And so that's what's happening here. This is straightening out the light. So that refraction pretty much goes away and the bird knows where to go to get the fish. So all aquatic birds have that little oil in their eye. And they also, besides having the oil in the eye, this little hare is smart. He's using bait.
He used to catch the fish, not the bird.
Yeah, he's got something. He's got a little something.
I know where he got the bread. I was waiting for the big one.
It's fattening up the fish.
That's nice, gotta try to eat that.
Yeah, now it's gonna go down.
Really paid off. First time I saw this behavior, Carol and I were off the coast of Africa watching a kite going around the coast of Atlantic Ocean somewhere flying, and it was dropping sticks in the water. I couldn't think I was dropping sticks. Little twigs and fish were coming up and I come down and shoot them. They didn't have bread, they just had sticks. Sticks.
False after.
And then we always said birds don't have a sense of smell, and we're learning better. Some birds do have a good sense of smell, especially seabirds. Seabirds here have, this is a special mechanism that certain categories seabirds have. And salt glands. The salt glands, and that's how they can drink salt water and spew out this. That's why you see them sneezing. They're actually just spewing out salt from their nose. But they also have very complex nasal. And if ever you've been on a what they call pelagic cruise, you get on a boat and you go out, 20 some miles and watch everybody throw up over the top. Been on a couple of times. Well, what should water they do on these cruises? At least a couple ones I've been popcorn, greasy popcorn. You'll see no birds out there. You throw this greasy popcorn out there in 5 minutes. The boat looks like this is from New Zealand. Birds are all over the place because they can smell that oil. And what happens in the real world, though, is they have these things called dinoflagellates. Dinoflagellates are little algae-like things with a silicon capsule over them. And there are enormous numbers, trillions and trillions of these things. And they're phytoplankton. They float in the water, sort of like plants. And then there's these zooplankton. These are little animals that are also floating in the water. And they're eating these things. And when they eat them, they crush them. And when they crush them, a chemical comes out, dimethyl sulfide. This dimethyl sulfide comes into the water. This is discovered by a woman professor at UC Davis about 10 years ago. Dimethyl sulfide comes out into the water, and that attracts fish. Because the fish now smell this, and they know, well, there's all these things here, all these zooplankton are good to eat. And of course, birds also then come and they know there's going to be fish here because they smell dimethyl sulfide and they know that attracts fish. So they come feeding too. And so they feed, they will also, they'll follow dimethyl sulfide trails all along the coasts where you find most productivity, and they'll usually follow them during migration so they know where the food is. So these birds are smelling their way through migration. And we know about turkey vultures and the black vulture. We saw these today. Black vulture here. These are the olfactory lobes right here. This is part of the brain. Olfactory lobe here in the black vulture, much bigger in the turkey vulture. Why? Because black vultures are predators as well. They'll eat live things. Turkey vultures rarely do that. So turkey vultures have to find their food by smell. Black vultures can see it by sight, see things moving around and go after it. So that's the big difference. Also the condors, Andean condor, California condor, they can all smell. African vultures, on the other hand, can't smell at all. They have no sense of smell. They have to find everything by sight. And then, okay, here's the ears. Now you can see an ear. You can't see it on the owl because of the feathers, but here's the ear of a vulture. And the ear of a chicken. And these ears are just like ours. They have a opening to the outer ear canal, and you have the tympanum, the eardrum, and the eardrum vibrate. But we have three little bones, what are they, stapes, incus, malleus. We have three little bones that are connecting this to the cochlea. In the case of birds and reptiles, there's only one bone called the columella, but it works the same way. This thing vibrates and pushes it and gets the cochlea vibrating. Okay, so we have sound coming in here, vibrating the tympanum, vibrating the stapes, vibrating the cochlea. Inside the cochlea are hair cells like this. And these hair cells go back and forth like this. They wave in the fluid that's in the cochlea. So when sound comes in here, it causes these things to go like this. And these are connected to the brain and you hear sound. In us, as you can tell by some of us, by hearing aids, as we get older, we lose our hearing. And the reason is we just wear out these hair cells, especially if you're listening to rock music or you're flying an airplane, you know, too close to the end or whatever happens to be. Machine shop. You lose these hair cells, and so you get deafer and deafer and deafer. Birds grow them back. We don't grow them back, but birds grow them back. And people are now, scientists are now trying to figure out why they're doing that. If they can do that, then we wouldn't have to wear hearing aids. And then, also along with this, we have these semicircular canals. Semicircular canals are in 3 dimensions, up vertical this way, horizontal, and horizontal this way. And whenever a bird or you move around like this, there are little bones in there, or little stones called otoliths. And think of a level, you know, a level with a bubble in it. You move it like this. The same thing in these semicircular canals. They're moving around, and so you know which way you're going back and forth. And birds do too. They have to have that, obviously, because they're flying in 3 dimensions. We're only moving in 2 dimensions. They're flying in 3 dimensions. And look at this. This is a clip from the dismal swamp of Virginia in the wintertime. These are red-winged blackbirds.
Who's doing the videotaping?
So here's another couple of shots. Here's one. Here's look at the shape of these things. Watch the shape of these things. These flocks like this. They will always look like a pizza. Think of someone tossing a pizza. So the pizza's flat, you know, not too thick, but it can flop around like this, right? So think of these things as pizzas. Because it's the only way birds can get together and fly around like that and coordinate and not run into each other so they produce any kind of injury. What's happening is that when you're walking in a crowd, a whole bunch of people on New Year's Eve or some parties, how many people can you keep track of that you're not going to run into? There's a limit, right? And it's with birds, it's 6 or 7. 6 or 7 birds they can keep an eye on. Same thing with you, 6 or 7 people. More than that, you start bumping into each other. The only way to limit 6 or 7 is to make that thin. If it was thick, they'd be right in the middle of it. So they make it thin. There's only 6 or 7 birds around it, and that's the way they coordinate all that. People found that out by using high-speed motion picture close-up photography. Okay, so those are a lot of the adaptations of birds to a natural world. What about an unnatural world, the world we've created for them? Some birds have adjusted somewhat. These guys, house sparrow, or city pigeon, the starling, and of course the crow. But the house sparrow, and the reason we're able to do that is that they're all over the place, is that the house sparrow, pigeon, and starling have in their native habitat were all over the place, all over Europe and Asia, just giant range of habitat. And they lived up in mountains, down in valleys, all over the place. So they had the genes to adapt to almost anything. So when they came over here, they adapted to almost anything. When did pigeons come over? Anybody know? Why did we bring pigeons over? To carry messages? No, the French brought them over for food. And they had dove coats and they would raise these things and eat them. They don't, of course, they don't do that anymore, but that's how they got here. The house sparrow and the starling were brought here in the 1800s by the American Acclimation Society, which is a society that was established to bring Europe to the United States. All this is a time of immigration. People would come over, like my grandfather did, and they wanted remembrances of the old country. So they brought house sparrows and starlings over, but also the guy, one other guy wanted to bring starlings over because he wanted to bring every bird that was mentioned in Shakespeare's plays over. And he brought quite a few over, nightingale, things like that, but the starling was the only one that made it. Well, house sparrows were being sold in 1880 for $500 a pair. You could ship them over from Europe in 1880. 20 years after they were imported, the city of Philadelphia had a bounty on them of 25 cents a piece. They can shoot them. They crow, you know, they're natural, but they've adapted pretty well. Barn swallows, 99% of barn swallows now nest in human-built structures. The generation time, 1.5 years, have been associated with humans for 2,500 generations. So, you know, they've adapted to us quite well. And then you've seen birds on the highway and you wonder why they get up and take off just before you hit them. Sometimes they don't, but most of the time they do. And the reason is they've learned. There was a study in France that found that they did on a bunch of roads. They found out that the birds figured out what the average speed was on the road, and they would take off early if the cars were going fast. They would take off later if the birds were going slow. And so they would, the researchers could go out there and they know exactly where a car was going to be before the birds took off. So they had learned. And then I think this is was a great study too. Cliff swallows build mud nests under bridges, under viaducts, things like that. This is under a viaduct over a road. And this couple professors who worked at a museum used to drive this. This is in Kansas. Used to drive this road back and forth, and they would, like I did for many years, they'd see a dead bird, they'd pick it up and then bring it to their museum and stuff it and put in their collection. So they did that for 20 years back and forth. They've been working on other things, but then they had this whole collection of fish swallows. I would say, well, let's measure them all. Let's see if there's been any difference in these 20 years or what happened to the cliff swallows. And it turns out what has happened is that there were more nests 20 years later. And there was more traffic 20 years later, but there was less mortality. So how do you get less mortality when even though there were more birds and more cars? Well, they measured them all and they found out that the latest birds, the ones they've been catching recently, the wings were 2 millimeters longer than the ones 20 years before. Barn swallows with longer wings are more agile than the ones with shorter wings. So the cars were making this whole colony evolve into longer winged birds.
Right. 2 millimeters.
And then pigeons, our old city pigeon here. City pigeons, if you notice, we'll look at city pigeons around. Every time you see a flock like this, you notice they're getting darker and darker and darker. There are fewer and fewer white birds, at least in the bigger cities. And the reason is that the melanin pigment that makes dark colors absorbs toxic metals, absorbs heavy metals. And so when the birds are eating heavy metal somewhere, they absorb it into their melanin in their feathers, and then they molt them out. But there's less melanin in white birds, and so they accumulate the heavy metals, and so they don't live as long. So we're going to get darker and darker and darker pigeons. And then you find that there's lots of birds are using cigarette butts in their nests. And at first it was thought, well, that's just, you know, it's just nesting material. It helps keep things together. It turns out that, though, there are less parasites in these nests because the nicotine from the cigarettes keep the parasites out. So lots of birds are building nests and putting cigarette butts in there. The problem is occasionally there's an issue with this. Birds have brought lit cigarette butts into nests and gutters and set buildings on fire. And birds have adjusted their sound, they've adjusted their songs according to whatever noise is in the background. If there's a lot of traffic noise, they use high frequency sounds because traffic noise is low frequency sounds. When the traffic goes away, they start using low frequency sounds again. And so they did in San Francisco, they determined that people could listen to recordings of birds and tell when they happen during the day, depending on rush hour. So if it was really noisy, the birds would just have high pitch. If it was really quiet, they have low and high pitch. So they're changing. And birds are adapting to a lot of light. We're talking about light pollution, and migration and so on. But lots of birds have adapted to light, and a number of birds they've found in Europe, at least, were nesting in street lights and traffic lights and so on. And they actually had more young who were more successful because they could feed all night long. So birds are really so well adapted. We've got all kinds of examples. I'll just give you one or two of how we have adapted our life to some bird adaptations. And one here is they've invented shock absorbers for computers, for tank helmets, for football players, for bike helmets, all based upon the structure of the woodpecker. Woodpecker skull's got a way of absorbing all these up to 12 G's of force. So now they got shock absorber. And then look at this. Here's a green kingfisher entering the water like this with a minimal amount of splashing around. And that's what the Japanese did. The Japanese studied kingfishers to come up with the nose of their super speed train. Okay, that's all I'm going to cover tonight. Thank you very much. I appreciate all your attention. Clarifications.
Any questions from the group here?
Yes, sir.
So those birds that feed on mammals, they have an advantage because do all mammals not see ultraviolet light like us?
The birds that feed on mammals.
Do all mammals not see ultraviolet light like we do?
Sorry, I didn't like hearing it.
I'm not hearing it either.
Do mammals not see in the UV?
Oh, mammals.
Does that give birds?
No, you know, some of the nocturnal mammals see a little bit better because they have bigger eyes, but they don't see UV. No. Just birds so far that we know of, anyway. Oh, my hair cells are gone. Okay, well, thank you very much. I appreciate
Some
it.
in the.
Oh, wait, oh, here. Let's see.
Oh, up here, somebody.
Okay, so far we just say thank you again.
Yeah, scroll up. There's a bunch.
Ah, there you go. Why do falcons have a?
That dark stripe that falcons have.
Good question. I don't know the answer. I have to think about that one, though.
What about
I'm
it?
sure there's a reason.
That one about the urine?
There's one also that is all year, all.
It's all urine. Yeah, I don't know.
Found, it's found.
There it is. It's all urine UV.
Yes. At least, well, all mammalian urine.
Birds don't have it.
Question in the audience.
Birds have they don't have urine. They have a different kind of composition.
So basically, if we take one of those purple lights, we could maybe see things. And you can do this moths and caterpillars, you know, the ultraviolet lights. You shine a ultraviolet or a black light on something.
Right.
It's talking about-
You'd be able to see whether it reflects UV or not, yes.